interesting one. There is another one. I'm at home, as you can probably imagine. I have another joke one. Let's see if I could find it. Here we go. So if you
Okay, what is this? Where are you sitting right now?
the the actual location of me right now is my home office, and that's what this would look like.
Are you doing experiments with all these things?
Oh, I'm just having some fun. Thank you.
Oh.
All right. I did want to practice doing some video. Now notice I'm on two, I'm logged in twice. One of my logins is where I have my presentation. And so just to be able to do that, I'll need to share. Oh, got to share that again because I have to make audio work. But more importantly, I've got a couple of videos.
Why doesn't every home in the US have solar panels?
Oh,
The
why
number
am
one
I?
reason is not about sunlight, weather.
In 2009, the University of North Carolina at Charlotte
I believe it all works and I am ready. And I will, of course, start up at the top of the hour or at the bottom of the hour as it is in your place.
Probably in the next month, I will be coming to USA, North Carolina.
Oh, yes. You mentioned that. Now,
I
you
will
said
visit your university during my visit.
you are welcome to visit. You do realize that the distance between Raleigh and Charlotte is approximately 2.5 hours, right?
Yeah. From Raleigh. I will be staying in Raleigh, and during June 1st or 2nd week, I will be visiting your university and UNC Wilmington.
Okay.
I'm planning to visit these
All
two
right.
universities.
I will send a follow-up email. I remember your request a little bit earlier, so I will send a follow-up email with with arrangements and instructions and the such.
Okay.
And I'm pleased to see that you have so many people involved in this.
Yes, 89 participants have joined so far. we can start the session in time.
I will wait for your 4 minutes, right?
Yeah. After 4 minutes, we can start.
Mhm. And as you can see, I dress for the occasion. Got my Indian jacket.
When are you planning to come in India for ABET accreditation?
Let's see. So the last time I was in India was in March 2020. So that
Okay.
was about the last time anybody really could fly between the two countries. Well, I know there's a lot of people flying now. But usually I come when I get an invitation and somebody could pay so for the flight and accommodations. So there's a couple of colleges and universities that have given me a standing invitation anytime. So I might be looking at maybe later in this summer or maybe even during some of our breaks that we have. But yeah, I enjoy going there. My last trip was to Delhi, and I finally got to go to the Taj Mahal.
Great. Our institution actually is not a degree awarding institution. So ABET accreditation, I think, is not possible here. But we are going for NAC and DA,
Mhm.
other types of accreditations.
And in fact, you never know. I may actually be in India in the fall because I usually do accreditation visits all over the world. And my first two were in India, and then I've also been to Jordan, Peru. I didn't get to actually go to Saudi Arabia because of COVID, but I reviewed a program there, so I'm on the list. So who knows? I might be in India, and if I do, I'll probably extend it a couple of days and visit some colleges while I'm there.
So during your visit in India, you just visit our place this time. You will make more better plan. Last time you have taken the workshop. So this time also we will plan for a workshop
Okay.
for at least 2 days for students.
Yeah. Oh, yeah. And as I've mentioned, I've done this a lot, especially Vijayawada, KLU. They've had me do student workshops with extremely large groups of students. Oh, it is 15:30. So shall I start up?
Yeah.
And do you do an invitation or there you go.
Pardon, sir. Am I audible to all? Okay, we'll be beginning with the third session now by Dr. James Conrad. Words may inspire, but actions create changes. With these words, which are apt for our today's speaker, I, Swati Nisnavde, Department IRO Coordinator, ETC, wish you all a very pleasant afternoon, and welcome our speakers, our dear participants and committee members to the third session of day 1 of IET approved International Faculty Development Program on 21st century recent trends, challenges, and future roadmaps for transitions in technological generation, organized by International Relations Office YCT, Nagpur, in association with Department of Electronics Engineering, YCC, Nagpur. A very good afternoon to all and a very good morning to Conrad sir. Dear all, today I have the honor to introduce our prolific and distinguished speaker, Dr. James Conrad, who would be enlightening us on autonomous vehicle navigation and robotics. Dr. James M. Conrad is an award-winning author, keynote speaker, and professor. He received his bachelor's degree in computer science from University of Illinois, Urbana, and his master's and doctorate degrees in computer engineering from North Carolina State University with a background in embedded systems. He is currently a professor at the University of North Carolina at Charlotte. He has served as an assistant professor at the University of Arkansas and as an instructor at North Carolina State University. He has been invited to speak to organizations across the world. He has also worked at numerous prestigious organizations like IBM, Sony Ericsson, BPM Technology. Dr. Conrad is a professional engineer, a senior member of the IEEE, and a certified project management professional. He is also a member of Eta Kappa Nu and the Project Management Institute. He served on the IEEE Board of Directors as Region 3 Director for 2016 and 17, and again as a director in 2020 when he also served as IEEE USA President. He is the author of numerous books, book chapters, journal articles, and conference papers in the areas ranging from embedded systems to robotics, including parallel processing and engineering education. A very important thing to mention here is we at YCC and the MJI Group have had the privilege of having him at our institution to guide us during October 2016. His devotion and commitment towards his research has inspired him to teach, develop, inspire, and mentor learners. Hundreds of students across the globe have been inspired by him, and his work continues to touch audiences from every walk of life. As mentioned earlier, Dr. Conrad will throw light on robotic and autonomous vehicle research. His talk will describe the history of his research, which is the conversion of a stock all-terrain vehicle to drive autonomously. He will describe how the Honda all-terrain vehicle steering, throttle, and braking systems were modified to a drive-by-wire system. He will then discuss how driving data were gathered and used in a machine learning environment. The results of this research will be shown in several videos that demonstrate how the vehicle can autonomously follow a paved or a gravel path in a forested environment. Now, without much ado, I invite Dr. James Conrad to deliver his talk. You are most welcome, sir. You can start.
Thank you very much. Thank you very much.
Pleasure to have you, sir.
And I believe I need to reshare. All right. So without further ado, I would like to introduce you to, oh, I got to hit the button that says share. Sorry about that. I would like to introduce you to some of the work that I've done, and what better way to do that than with a video. So I would like to show you this first video.
Fun. All right, go. 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 Drive it. Sweet. That's weird. It's like an animal.
Like we're being herded by a mechanical dog.
Yeah.
You're like Jimmy Neutron. Just go tighter and tighter.
should drive it to the gas station. We should put air in the tires like that.
Unlimited card in here.
Oh, I can order 15 seconds.
I've got the whole thing so far, a minute 15. But I don't like this. I don't
All right, I believe you get the idea of what I'm about to talk about. What you just saw there was a picture of our autonomous all-terrain vehicle, also known as an ATV. This is a device that we've been working on for literally 15 years, and that is actually the results of the first phase of the work, in which we were able to drive it like a remote control vehicle. So, welcome from the United States. One thing I should mention to you right now, I'm actually logged in here in two places. My camera and my audio is at this computer, and then on this computer that has two screens, I'm actually running my slides, and so you may see me turn away every so often, and that's because I'm working on the presentation. So first, I'm going to just let you know a little bit of who I am and some of the research I do. Then I'll talk to you about the whole history of this all-terrain vehicle project, its project definition, why we're doing it, and then go through the different phases of how we actually got this vehicle up and running, keeping in mind that this is a vehicle that is intended for somebody to sit on and drive, so it's not immediately designed to actually be an autonomous vehicle like the Teslas are currently made. And then we'll talk about how we're using machine learning and control of the steering and the throttle, as well as braking, to be able to follow a paved path or a gravel path through a forest, and then I'll finish up with the discussion and conclusion and answer any questions that you might have. So first of all, who am I? I have been to India many times. I think this is, if you look carefully in the corner, it says Walchand College of Engineering. I've been to India, I think 7 times, not including visits like this. I'm at the University of North Carolina at Charlotte. I'm a professor of electrical and computer engineering, but I've also worked in, as mentioned in my introduction, in several companies. So I come to teach my students with an experience in developing mobile phones and display products at companies, as well as the first desktop 3D printer, and I consulted with robotics companies as well. If you were to come to UNC Charlotte and look at my lab, you will see that I have equipment and development environments for companies like Emerson, the Electrical Power Research Institute, iRobot, Zapata Engineering, National Instruments, and my over 125 graduate students that have done research under me are in companies all throughout the world, including Tesla, Lucid, Qualcomm, Texas Instruments, Intel, Seagate, MathWorks, a lot of companies all over the place. Our area of expertise in our lab is with microprocessor, microcontroller-based systems. This is expanding now into, I didn't list it here, NVIDIA. And I say formerly Cypress because it was Cypress, but now Cypress has been bought by, and I can't remember who all these companies are keeping on being bought from. I think Xilinx was bought by NVIDIA, right? But we do work on embedded systems and software. We use sensors because sensors and actuators are an important aspect of my other area of research, and that is robotics. Everything from autonomous robotics and all the way up to humanoid systems that I've have and developed in my lab. This picture right here is an example of one of the projects that actually a undergraduate student group was looking at, and that would be in the United States. There is a concept where we put our clothes in a clothes dryer, press the button, and instead of hanging it up outside, it goes through and dries the clothes in our clothes drying machine. The vent for that clothes drying machine often gets clogged with lint. And this was a robot that was designed to be able to crawl through that dryer vent and clean it along the way. If any of you are familiar with the robot called Stakito, I am the Stakito guy. I've been working on this since 1984. And I'm sure, sorry, 1994. And originally it was a very simply hand-controlled small little micro robot that looked like a walking stick. But I'm with work with a lot of different students. We investigated being able to put a microcontroller on top of this vehicle, and this shows a different path through the design as I chose more processors and refined the prototypes for this eventual system. The important thing is what you see here in the final picture, and that would be over here, right there, would be a small little robot that based on not the thicker of these two wires, but the thinner of these two wires, would be able to take steps and walk very much like a six-legged insect would actually walk. The reason why this is rather interesting is because the IEEE has published 3 books that I wrote, and these books describe this robot and how to build this robot. And also inside the book itself are all the parts to build this robot. So right now I want to talk to you about all the different research that I have going on in my lab. I'm going to zoom in on my final, or I should say probably my largest project right now. So the different things that I have done recently in my lab include these 5 listed topics. Robotic vacuum cleaner is one of the more interesting and commercial aspects of this work, and I'll talk about a lot of these in detail. The first is building a swarm of quadrotors. If you're familiar, a quadrotor looks like this, and the objective is if you want to have a swarm of these fly and do it autonomously, you need to give it, of course, enough intelligence to be able to determine its location, its pose. Robotic pose would be how it faces. But more importantly, if you wanted to work autonomously in a swarm, you need to have each one of these individual quadrotors able to identify where the ones next to it are. And if you look at this configuration, there's really a possibility of a single quadrotor to be able to look in its 4 major directions, and that's not even up and down, it's just to the left, to the right, in front of it, and behind it. And each one of these X's represents a individual quadrotor, and then each one of these other ones are a quadrotor with a bar, and each one of these little balls that you see right there is actually an LED. And the whole idea is that those are beacons that a quadrotor that has a camera is able to look at, and based on its computed distance between the center of each one of these individual LEDs, is able to determine how far away the next quadrotor is to it. And this is because with the accuracy of GPS, which is not that great, especially for flying vehicles like this, especially for lots of flying vehicles like this, as well as the possibility of using cameras. What do you know? We use cameras, but specifically a beacon that allows us to get a better resolution of how far something is. You have several papers published on that, and you can feel free to look at my online bibliography to be able to read about this in more detail. Another area was the area of intelligent transportation systems. If you think about your typical Tesla vehicle or something very similar to that, all of these vehicles have lots and lots of electronics on board to be able to help it determine its location, its pose, and information about its surroundings. Well, the unfortunate thing is there's an awful lot of vehicles out there. I have one. It's a 2011 Toyota Highlander. This vehicle does not have all that intelligence built in inside, and it really doesn't know where it is. So you will need to actually introduce to these legacy vehicles additional information and additional equipment to be able to allow it to communicate with the other vehicles and the infrastructure itself in our new world of autonomous vehicle navigation. And so in this case, we trialed out using, in fact, our ATV, a system where we could gather the important, valuable information from the vehicle that we're in and convey that to the infrastructure, that being, in this case, we trialed it with a Raspberry Pi-like environment on a roadway, and used the OBDII interface in a car. That would be the interface that people typically check to see if there's something wrong with the engine, but you could also use that to gather lots of information from the surroundings. Another one is I had a graduate student work on man-machine collaboration, and this is all in support of my ATV project later. One of those would be the concept of, if you have a all-terrain vehicle or something else like that traveling along, it could do its own major, or I should say minor navigation, avoiding trees, following paths, whatever. But sometimes it needs to know where it should go when it reaches a particular location. Maybe there's a deep ravine that it cannot figure out how to get down. And so it could ask a man that is traveling with it nearby, okay, should I turn left or right to go travel and find a place to cross this ravine? And we were investigating how one would go about this man-machine collaboration. I also worked with a company on autonomous vacuum cleaners. They did not have their own autonomous feature, and so we all go ahead and got a sample running environment in iRobot, in fact, and identified what electronics and especially what software to be able to run, to be able to navigate, not like a Roomba. A Roomba is a vacuum cleaner that bounces, well, the lower levels bounce off walls and eventually clean your entire room, but it does it in a random fashion, versus others that actually do a full sweeping action. In other words, very similar to how one would go about vacuuming a floor or cutting a lawn, where you visit every area in your floor exactly once, and you do it in a more methodical reason. In that research, we actually used all the actuators and sensors in a typical iRobot, iCreate environment, or I should say test environment or vehicle environment, and we interface with all of those. I should add one last investigation area that I forgot to put in here. as I was making my slides is what I call a breadcrumb network. And for those of you familiar with the fairy tale of Hansel and Gretel, I guess I should ask the audience out there, are you familiar with the Grimm's fairy tale story of Hansel and Gretel, where they leave a trail of breadcrumbs in the forest? The objective is they put down these little breadcrumbs as they're walking into the forest so that they could perhaps follow that same trail on the way out. Unfortunately for them, breadcrumbs are very delicious for birds, and the birds ate them. But in our story, we have small little modules, and in fact, the small little modules are very similar to what you see right here. These small little modules we were using to place in a forested area, and the objective of that was we could lay down a trail from our source to our destination that later a autonomous vehicle could follow to be able to find its direction into a forest that may have GPS denied areas in heavily wooded forests in the United States and other places around the world. Because of the tree canopy, you are not able to get a decent GPS signal to be able to localize yourself. So that brings up the initial problem definition of our biggest project that we were working on. And that was, we had a company, Zapata Engineering, that wanted to have a rugged vehicle, which meant an all-terrain vehicle, that would drive through a field looking for unexploded bombs underground. And the problem statement was that in the United States, nearby, there is a military base. It's called Fort Bragg. And during World War II, they used a specific area of their military base for practice bombing runs for their new pilots that would then be sent overseas for deployment in Europe or in the Pacific. Well, a lot of these bombs exploded, and many of them did not. They actually buried themselves into the ground. And you imagine this is in the 1940s. And so still to this day, there's all of this metal and all of this possibly unexploded ordnance underneath the ground. And so they wanted to be able to have a vehicle very similar to this, pull behind it what's called ground penetrating radar, look for this ordnance underneath so that it could tag it, and then later a removal team could come in and fetch the items. Well, the solution was an autonomous all-terrain vehicle that would be able to pull this trailer and in the process avoid trees and rocks and ditches, and be able to examine every square centimeter in this bombing range that they intended to look at. And so that's the problem statement. A good complete coverage planning idea would be very similar to what you would see here. In this case, you have your starting position, and it would continue in a very methodical way, but there would be a problem, is that when it was approaching a particular way, you would have to, it would not be able to actually drive into the water. In this case, it would have to go around. And so part of this would be to identify how one would avoid obstacles, especially in fields. In this case, our solution is that we're looking for complete coverage. This vehicle will be navigating top to bottom, as you saw in the picture. The borders are reachable. You want to do, as I said, the maximum coverage. And the trees and ravines and lakes, etc., are obstacles, and ravines will be very similar to what you see here. And so in this case, we had investigation of path planning, as this turns out to be. And this is as opposed to classical path planning, where you want to go from location A to B in the fastest way possible. Again, this is path planning when you are literally planning a fairly large path to be able to cover the entire area. And so in this case, our investigation was to allow this, and this is in the Turtlebot simulator, hence you see a small turtle right here in the middle, would be to create a path plan for identifying that you can visit each one of these squares, and where you couldn't follow those squares, you would plan a path around those obstacles that were in the way. And that's some of the research that we did in support of this project. So as a part of our phase one, we had to take our all-terrain vehicle, as I mentioned earlier, and modify its subsystems, specifically the steering, the throttle, as well as the braking. And it's not as easy as just, oh, we'll just put a wire there to connect to a computer. There were situations where we had to mechanically add things. For example, in our older ATV system, it was the time before a lot of electric vehicles. Braking was handled via a hydraulic system. Press a pedal and cables or a hydraulic fluid would activate the brake. I believe in our vehicle it is cabling and not hydraulic. And so we needed to find a mechanical way of being able to do that. We also needed to find a mechanical way of having more gasoline go to our engine so that it would speed up. One thing we didn't have to worry about is having to change gears in our vehicle, because our vehicle was going so slow that it did not need to go faster than approximately 10 miles an hour. So as a part of our phase one, we introduced a central controller board. We used the Renesas processor. We also introduced a 40 amp H bridge that actually did wire into the power steering assist motor. And we did have feedback there with a rotary encoder attached to the steering column. We created a subsystem of braking where we had a physical mechanical linear actuator able to depress the brake pedal. And then we also had a servo that we controlled to allow the throttle wire to move, and hence make our vehicle go faster or slower. Now, we interfaced all of that with a laptop with a camera, LiDAR, and GPS. And by the way, we controlled all of this just to make sure it would work with a remote controlled transmitter. And of course, our system had a radio receiver. And so when you go back and you look at this vehicle, and if we looked at one of the earlier pictures, let's see, here we go. I think this gives you a good idea. We do have up front, we have the laptop itself. We have a LiDAR, GPS, and then we have all the control systems that are actually, in this case, underneath the seat, and we've built into this area. We added an extra battery because, as it turns out, this LiDAR, which is a very good industrial LiDAR, works at 24 volts. So to get 24 volts out of a 12-volt battery, you could either step up the voltage, or we wanted to be a little bit more judicious with how much of that energy we used, and so we just added another battery and put it in series and got ourselves 24 volts. Now, as I mentioned, we worked on the throttle. We added a servo to the air intake valve, braking, linear actuator, and I would say that the initial version of it was a rather more difficult solution. But later on, we actually we used the word spoofed. In other words, we made the steering assist module think that it was getting a signal from our processor, but in fact, or from the actual steering. So I should mention really quickly, some vehicles are equipped with what is called power steering. In a power steering system, the system itself will amplify your actual turning of the wheel. And in this case, since we have handlebars that you are turning, that is very much what the steering assist module does. It helps make the steering easier by adding a motor as well. So you still have to turn the handlebars, but the steering assist device will make it easier to turn. I showed you the video of that already. Now, unfortunately, during this whole work, there was a downturn in the economy of the United States as well as around the world, and we lost the funding to finish the project to make it fully autonomous, and their funding was pulled anyhow to do this work in the Fort Bragg area, and so we changed the direction of what we were doing to work on another Department of Defense or another a military application, and that would be to follow a path in the forest. Now, I should say it could also be used for search and rescue or other aspects as well. So when you're following a path in the forest, the expectation is that the pathway is pretty clear. There's not very many obstacles. If there would be a small animal in the way, it would probably be scared away from the vehicle anyhow, and that we would not have to run it over. And the expectation is that there would be very few, if any, fallen logs or anything else like that in the path. So another aspect of that is, as I mentioned earlier, you can follow a breadcrumb path in the forest. If you did not have an actual path to follow, and that would, of course, introduce the ability of, or the need to actually do obstacle avoidance because you wanted to avoid trees in the way. And then, of course, you could also travel towards a specific GPS waypoint as well. So in our phase 2, we redesigned our entire system. Now we're going to, or we decided to use a CAN bus. CAN bus is used extensively in the automotive industry. And the reason why it's a very popular standard for the automotive industry is that it has a differential two-wired system in which a specific 0 and 1 is represented by opposite voltages on two different lines, and using that is able to alleviate a lot of the noise that would be present in a typical automotive system. The downside of a CAN bus is it is a rather low speed bus. I believe it is recommended no more than about 1 megabit per second. So if you look at the environment that we had enabled here, we are looking at compass, LiDAR, 2 LiDARs, in fact. One LiDAR that would be looking straight, and another LiDAR that would be looking more down at the ground. The one down at the ground is so that you would avoid large holes and ravines, and one looking out at a level horizontal surface would be more for the obstacle avoidance of trees and other such devices. One thing that I want to point out here that you do not see is a camera. And that is because the original design was looking at doing all of this without the use of a camera. which did change later. This is all, each one of these individual boxes is a distributed processor. In our case, we chose Texas Instruments MSP430 devices as the interface device. So in fact, this throttle, this braking subsystem, this steering subsystem, this compass, and this GPS all have an MSP430 and CAN bus interface with it, as well as, I should say, the LiDARs as well, is that we use the same processors, same processor board, and let's see, I believe these are about the same picture, right? Well, it's the same thing. I go into a little bit more detail about what these are. Well, let's show a picture of what these all look like. And so using a CAN bus, which, by the way, our CAN bus was also bundled with the power and ground signals associated with the need. So we were able to distribute power via this same cable. We were able to build up a lot of different boards and distribute them across the entire body of our all-terrain vehicle. Yep, I think I said everything right here. Now, part of this project, we also created a application programming interface library, and that would make it easy for us to use the same code base for all of our processors and bring in whatever library was important to be used, or functionality to be used with each one of these individual modules. If you remember, these are the modules that we had identified that we would use. Each one of these individual modules could, well, I went back a little bit too far. Each one of these individual modules could use within it I2C or the SPI or the UART communications protocols. And the advantage of this is I've actually been able to use this API and teach my students in my advanced embedded course how one would go about developing an embedded system using only application programming interfaces, not worrying about a lot of the lower level activities that a microcontroller can typically, you could usually use in C for the microcontroller. So now it's time. I've been talking long enough. Let's look at another video. I always love looking at videos in my classes. So in this one, I'm going to go over this, and here's hoping I don't get another commercial.
In 2009, the University of North Carolina at Charlotte converted a Honda 4Trax Rancher ATV into a fully remote-controlled ATV. In order to make the first steps toward a fully autonomous ATV, the following subsystems needed to be developed. The operator is not controlling the throttle, but instead having his finger on the kill switch. Here, the ATV is pre-programmed to drive forward at full speed for a predetermined distance. The rider on the ATV is not controlling the vehicle, but instead positioned to shut the vehicle off in case it were to venture off course. Here, the ATV is pre-programmed to drive backward for a predetermined distance. Lastly, the ATV was pre-programmed to follow more complex patterns, such as a figure 8. As mentioned before, the operator that is following the ATV is not controlling the vehicle, but instead is there to kill the program if anything were to go awry.
Many people don't know this, But if you qualify for this new offer,
I don't need to see that. I do have yet another another couple of videos. I love videos, as I said. So our phase 3 was to they'll make this totally autonomous. And the whole idea is that we wanted to, as I said, follow a paved or a gravel path. But this time we introduced a camera and used that camera and a couple of AI models for being able to learn what a path looked like in a forest. And then once it had been trained, to actually follow that path in the forest. So we're using a method to localize the ATV specifically on the path itself. We used the camera and semantic segmentation of that camera data to identify in the particular frame where the path was, where the trees were up above, where the grass or other ground surface was, and even identify what the sky might be in that entire image. We also, in the process, developed a data set for that entire path. In other words, we actually went through and drove a couple of paths, different areas of it, quite a bit of data associated with that, and we are in the process of making that available online. So if other people wanted to use that for their machine learning models, they can do that as well. So now we have modified slightly what you saw earlier. Now we have again, the CAN bus, and now we have an NVIDIA Jetson Nano that is connected to an Intel camera. This camera is able to identify not only regular image data, but also has the capability of storing accelerometer data as well as LiDAR data. I should say a rudimentary LiDAR, 3D LiDAR is available with that camera as well. And it is attached via CAN bus to the operational parts of our system. We did make a few modifications. Probably one of the more major ones is that we're finding that our steering control just did not work well in the forward direction. You saw it work quite well in reverse, but it turns out that we just did not have enough energy to overcome some of the linkage problems, mechanical linkage problems that you find with all-terrain vehicles. And so if you could see very carefully here, or very closely here, we added a motor as well as gearbox, pulleys, wires, etc. And we actually are using a motor to pull the handlebars. We're still using the steering assist motor to help us with the actual steering, but in this case, we have added a motor to be able to move the handlebars. It's not a very elegant solution, but actually, in the end, this is the third iteration of a steering solution. It actually turned out to be one that is the most not only energy efficient but least damaging for our steering assist motor. So if we look at what our AI model is like, we went through the process of data gathering. We pre-processed its semantic segmentation, and in the regression, we're able to identify how our system should work. So we all did this not hands-on, but in a simulation. And so there's another opportunity to bring up another video. So let's take a look at this.
In 2009, the University of North Carolina at Charlotte converted a Honda 4Trax Rancher ATV into a fully remote-controlled ATV. Recently, the ATV project has been picked up again with the hope to enable autonomous driving. In this clip, the ATV is pre-programmed to drive backwards for a predetermined distance. Once simple maneuvers were working at a satisfactory level, the ATV was given more complex paths to execute. Here is an example of the ATV driving backwards autonomously. In the previous videos, the ATV has had no way to see or sense its environment. This is where pathway identification comes into play. Here is our proposed solution and implementation to enable the ATV with pathway identification. First, 2 cameras were mounted onto the ATV. Second, an expert driver drove the ATV at a constant speed in the center of a path. While the ATV traversed the path, the cameras recorded and stored the data into a file. The data was processed using semantic segmentation, which can be seen here. The process video that you see on the right is broken up into different classes. For example, the purple indicates the path, while the darker green indicates the trees, and the lighter green represents the ground outside the path. Once the semantic segmentation of the video is complete, an inverse reinforcement learning model is used to identify the different sections of the path. As seen in the figure, the path is broken into sections, which consist of left outside, left inside, center, right inside, and right outside. The learning model uses these distinctions to help indicate rewards. Once this was put into place, more data was gathered where the driver drove off the path. Semantic segmentation was applied and can be seen here. Going forward, more data needs to be collected, and the plans are in place to make this happen. However, when the new data is recorded, we will also be recording the angle of the handlebars, which will be used in conjunction with the video footage.
All right. So when we gathered data, we looked at an area behind our building. I'm actually my offices are in this building here called APIC. Actually, this small little sub building right here is a garage where we store the all-terrain vehicle. So we're able to pull our vehicle out of the garage and move over in this area. There's a specific path, and we use this path for doing the training and actual execution. We gathered 41,000 frames associated with traveling this path. And in the process of traveling this path, there were areas that were, as you can see over here, full ground, actually is at the edge of a pond. And so we were able to identify the pond, and then more heavily wooded area here, including a area over here, which, by the way, this is a paved path with asphalt. I believe most of you should be familiar with that material. But also a path over here was associated with gravel. And in fact, a lot of the path that we followed was associated with a paved path with a small little strip. And you can kind of see this over here of gravel along the side. Several methods of trying to identify what the path looked like or how to identify the path were attempted. And one of those includes the canny edge trigger, which was not very successful, as you could imagine from the results from this analysis up here. We tried everything with color filtering, combining both Cityscape, ENet semantic segmentation, and SegNet ResNet 18 to identify the path. And in the end, the ideal one turned out to be the semantic segmentation. You saw part of that in the video earlier. It turned out that our best application was by training with the Deep Scene database. That is a database that is associated with traveling paths in a Germany forest, I believe, and using the tool SegNet, but all doing this at a low resolution. One of the aspects that we found is that if we tried to do this with too high resolution, our processing time was just way too much, and we got much better resolution if we relied on, or I should say, we got much better response time if we relied on a lower resolution, and that would be a process in which I'm trying to remember the resolution aspect of it. I think it was 480 by 280, but don't hold me to that. As opposed to a high resolution, which was 1080. And in this case, if we were traveling at 10 miles an hour, we were able to respond to steering instructions at the rate of 18 centimeters per ability to process. Now, as opposed to what you saw in the earlier video, we actually gave our identification of the pathway a little bit more resolution. So instead of 3 areas in the pathway, like we showed earlier, one was center, right inside, and left inside, we further divided it into another 2 regions, with, of course, region 3 and region -3 to be the what previously was called right outside and left outside, to give us a better resolution. We're also using in our machine learning algorithm 2 points to identify where we currently think we are and where we want to be compared to what our steering is telling us we're going to be. So the best thing to get out of this is that as our camera image identifies based on this, the edge of the path, we're able to tell our machine learning algorithm it would be better to steer a little bit to the left, because in the future, it looks like you're going to be driving off the right side of the path. And so in our training session, we used or tested least squares and least mean square models. And in the end, we found that least squares worked out to be best. Of the 41,000 images that we had gathered, 33,000 were used for training our machine learning system. And then we used 7.7K of these images for testing. And I believe you've seen this already. This was described in the video, the process that we used for being able to identify how well we stayed on the path compared to, in this case, an expert driver versus, and this is how we tested our data versus the expert. We used additional images to be able to say, that wasn't a good job at driving. The steering should go this way. If this works out well, it does. This is an example of the actual video stream that we have. And this is, for example, telling the machine learning system where it is and what the steering angle should be to get back on the path. You notice that, for example, we're about to get off the path, and so it's -1 says you should steer a little bit to the right. In this case, it's saying that, oh yeah, it's going between 1 and 2. You should steer more towards the left. Sometimes it switches back to 0. That's part of the learning that we had along with this algorithm. But again, we relied on the algorithm being able to determine when was the appropriate way for it to turn. So finally, once we had simulated this, or tested it in simulation, we tested it in real time. Our pipeline is such that our camera is fed into a segmentation algorithm where it identifies the states. The states are fed into our machine learning trained system, which then actually identifies the angle at which the steering wheel should be turned. I should add that the speed of our entire system was assumed or was desired to be a constant speed. And so we had a completely different subsystem, which was trying to have our speed of the vehicle go as close to 3 miles an hour as possible. We actually found 3 miles an hour was our average, what we call the sweet spot, or the best speed to be able to travel as square or as center as possible on that line. Let's see. Yep. In the end, all of this work was done on the NVIDIA Jetson Nano, and then when the angle was identified, I'll answer that question when I'm all the way at the end. How about that? I saw a question come in. All of this was done by the Jetson Nano, and then, of course, as I said, the actual angle that we requested this to be sent was, or to be turned, was actually transmitted via CAN bus to the steering module. The real-time results found that, as I said, using least squares with SegNet was the best. Steering response was narrow. It was mostly working. We found out we were going too fast. Unfortunately, our training data was a bit biased to the center position, and not training the models for the edges caused a few problems. And so our solution was that we amplified the deviation from center value such that we made it even less desirable to be along the edges. And we then trained again the machine learning model. And we added, what we did is we augmented our original 41,000 images and create I should say 33,000 for the trainer. We augmented it with basically multiplied it by 4, and we found that we did not really have a need for that additional data. Our 33K entries for training were sufficient. The result is the amplification was a good solution, and more data did not enhance the model. So this is our old real-time results. We have now learned how to do a shut-off device wirelessly instead of wired. It was able to stay online, but my research assistant running beside it, and this is also, as I said, this was going a little bit too fast. I'm just so happy he didn't get hit in the process of traveling or of testing this. So again, as I mentioned, we reduced the ATV speed from 6 down to 2.9, roughly 3 miles an hour. We looked at what was going on under the covers, and to some of the things we found was that cracks across the path were leading us to have occasional very jerky actions with the steering. And so with that, this noise, we improved the ability for segmentation, in other words, to identify the path to not just a couple of points, but a whole bunch of points, and adjust the steering that way. Our final result is in this video, and I see I am at about the max. So I will try and view some of this video. Now I have to apologize for the shakiness of this. So as you see, there's no driver on this vehicle. And as it's driving along this path, it's kind of a worn and cracked path if you look at that. It is able to identify here the path compared to the ground. And you notice there is a pretty good turn here that it has to make, and it stays on the path. And as my graduate student that worked on this will be apt to say, I was very happy that this all-terrain vehicle did not take a swim in that pond that you see on the right-hand side. This is, by the way, sped up, I believe it's 2.5 times, because otherwise this would be agonizingly slow. As you can see, it's able to identify the path. It's able to avoid going into the lake. Even though it passes some bricks on the left-hand side, it didn't think that that was a path. However, later on, it will identify that gravel. And in fact, this is an example here. It sees a gravel over on the right-hand side for another branch. And it kind of figured that was part of the road. Now, as it keeps traveling along, you see there is gravel on the side of the path, and then there will be a branch. And since we actually didn't program it to, by the way, notice that it's really hugging the side where there's a lot of gravel. That's because it can't identify asphalt and gravel as being two different materials, and so it's trying to keep the center of all of the material. And you notice here, even though the paved path goes off to the left-hand side, it did identify that it wants to travel on the gravel, and it went on the right-hand side. And I'm going to show just a little bit of, while I'll answer this, while building the ATV, how you take care of storage of huge data. So if you think about how much data we actually collected, the camera data, we just, as we were driving the vehicle and we took the data, we stored it on just a simple flash memory device, because not only that, but we also collected data of the steering. And so we had a lot of image data that was easily transferred to an extremely large 2 terabyte device. And when we are actually running in this situation right now, we are not actually gathering any data. I should say we are not storing any data. We are gathering the image processing, or we're gathering the image data, processing it as it runs, and just not saving it. And so that's the data storage is with respect to our actual running, is we're not storing it. And the computing model is as I said, a Jetson Nano, and it is running our semantic segmentation, as I showed earlier, as well as the trained machine learning algorithm. All right, I think we've seen enough of that. I'm going to go ahead and turn that off and go back to my presentation where I'm almost done. The caveats: we can work in light fog, haze, light rain, cloudy weather, sunny weather, asphalt, gravel, and it could turn pretty sharply. Now, the average speed is 2.9 miles an hour. It goes, as I said, faster and slower. And we can handle up to 9 miles an hour. Results are not as good. We don't perform well in low light situations. So we found that our camera that we had selected does not work well near sunlight and near sunset, I should say. and also in heavy rain and dense fog. And so that is one of the unfortunate aspects of this is, and it's really all dependent on the camera that you use compared to the machine learning data that you have. We didn't test in snow. Those of you who are familiar with the joys of snow, we did have one snowstorm during the process, and unfortunately, when you cover a snow or when you have a path and it's covered in snow, you can't really identify the path. So no, it probably wouldn't have worked anyhow. It's not designed to handle forks because obviously there's a higher level of artificial intelligence for that. Higher level meaning if I, a human, am walking a path, I know I need to walk one way or the other. And a good question, how is live object obstruction to be handled? We actually don't do that right now. So that's part of the things that we're going to be doing in our future work. So in the end, our internal combustion engine was transformed to an ATV. We use segmentic segmentation and image processing to find the ATV pose to keep it on the path. And we calculated the steering angle to keep it on the path. Keep in mind that the main difference between our vehicle and like a common autonomous road vehicle like a Tesla or something like that is they often rely on lane markings and GPS and other traffic schemes to localize itself and identify its pose. And we found that the ATV was able to maintain its center point 91.5% of the time compared to what a human driver would do. And more importantly, is it stayed on the path the entire time. It didn't run off the path and hit a tree or anything else like that. Future work, man, I tell you what, controlling a gasoline engine is really difficult. And so in the end, we learned that we would much rather have an electric all-terrain vehicle because it's a lot easier to control its throttle. And so we're gonna look forward to using a vehicle like that. We're going to integrate this machine learning model with breadcrumbs, be able to follow which way to take one of those forks in the path. And then we need a faster GPU to gather more data while we're moving so that we actually can get better resolution. And then, of course, integrate obstacle avoidance because we currently don't do that. In the end, I would like to thank you for your time. By the way, this is a picture of me in Chennai or the Chennai area, Tamil Nadu. This little guy kept on nudging me. He either wanted food or he wanted me to pet him. I hear it's good luck to pet a cow on the head. So with that, I will now open up for questions. By the way, this is my contact information. If you want to know more about some of the research that I do, you can feel free to visit my webpage. I'm easily Googleable. I do believe I got 3 questions, and I believe I've answered all of those. If you want me to ask or answer further questions, feel free to type them in.
Participants are requested to put their questions in chat box. I'll read them out for James, sir. Participants, if you have any questions, please put them in chat box. So we have a question here. Rakhi Vazgi ma'am wants to ask that initial version of ATV was rule based or something else, and how you have build knowledge base for initial versions of ATV.
All right, so that's a good question. One of the things to note is, remember, I don't know what you mean by initial version. I believe phase 1. Remember, phase 1 was all controlled with a handheld controller, and so the handheld controller really was just responding to a driver. Now, I don't know if all of you have this toy available for you in the US, but we use the exact same system for a small little remote control car that you can race on dirt paths and other things like that. We just had a lot bigger vehicle to drive with this handheld controller, and so the rule base was nothing more than us giving instructions, turn left, turn right, whatever. So the phase 2, that was perhaps another initial version. It was rule based, in which we said, okay, drive forward for 3 seconds and then brake, or drive in reverse for 3 seconds and then brake. And then if you remember the figure 8 signal, we literally said, okay, now turn the steering wheel 30 degrees and travel in reverse for 5 seconds. Then turn the steering wheel 30 degrees the other way and drive another 5 seconds. So I guess that would be considered rule based. So not until phase 3, where you saw the final results there with the vehicle traveling on the dirt, the paved path, was it was a true machine learning. In other words, not even rule based. It's in your machine learning algorithms and training, et cetera. You're saying this is good, do this, and this is bad, don't do that. Well, in our case, it was just inverse reinforcement learning, and so it's kind of like, this is good, only do this. I think I answered the question, right? All right. I see a lot of kudos and thank yous there. Thank you very much.
If you have any more questions, participants can put them in chat box. Okay, a lot of thank yous for you, sir. Okay, I think we don't have any more questions from the participant side. Right. So thank you so much, Dr. Conrad, sir, for introducing us to such an interesting topic. I'm sure you have definitely encouraged the participants to pursue area in this work. And thank you for all your valuable inputs. And we are extremely grateful that in spite of the time difference, you have delivered this session according to our schedule. And I request you to accept a token of gratitude on behalf of the organizing team and Yashwantrao Chauhan College of Engineering, Nagpur, for sparing your valuable time and guiding us. Thank you, sir, once again. It was great having you here.
All right, thank you. And I would like to ask the organizers, I can make these slides available. I would assume folks might want to look at them later.
Yes.
So if you can give to me information about where I could upload it. It's a little bit too big for a an email, so I'll wait on that information later.
Yes, we will send you that information so that you could upload the PPT so that participants can have a look at it later on.
All right, sounds great.
Okay, thank you, sir.
All right, thank you
so much.
And
thank you so much. Great to have you.
And I will say so long, everyone.
Yes.
Requested to all participants, please turn on your videos. We have to take a screenshot. Just a minute. Okay, thank you all participants.
Dear participants, we conclude here today. Tomorrow, our first session will start at 10 a.m. sharp. So it is requested to use the same link which was provided today to join the session at 10 a.m. sharp. Thank you all.